Okay, question 2. Okay, so figure 3 shows the label from a box containing radium-226. Radium-226 emits alpha, beta, and gamma radiation. Alpha, beta, and gamma. Okay. Handle only with forceps and always directly open end away from person. Right, so that's all the information given to us in the question stem. Figure 2.1 shows how the activity of radium-226 will change. The activity in Berquell, time in years. Determine the half-life of radium-226. Show you're working on figure 4. Show you're working on figure 4. Right, you have to use a ruler and mark your values. Now, in pencil, I'm just going to try and very carefully work out exactly the value to start with. So, these jumps are 20,000, and you've got 5 spaces. You've got 5 individual squares between each individual jump. 1, 2, 3, 4, 5. So each little square is worth 1/5 of 20,000. 20, 1, 2, 3 divided by 5 will tell me the size of each division, and the size of each division is 4,000. Right? So I think we've got 180,000, right? So it's 184,000 to start with. So this value here is 18400, right? So I need to get to half that value for one half-life to have passed. So 184 divided by 2, 92,000, right? So I've done 184,000 divided by 2 gets me 92,000. So I need to go to here to read off where 92,000 is. Well, if this is 80,000 and this is 100,000, then 92,000 is going to be almost exactly in the middle, just slightly higher. In fact, I think that is exactly 92,000 now. Now, using a ruler, I'm going to draw a line across from the 92,000 value and draw a line down from where it touches the half-life curve. Okay, so I'm getting a value here of, again, I'm going to have to work out the scale of the graph. So here 10 divisions is equal to 1,000, so each division is worth 100. So this is 1,100, 1,200, 1,300, 1,400, 1,500, 1,600, 1,650 maybe, okay? 1,650 years. 1,650 years. Right, so the marking for this, I would imagine you get marks for things like showing these on the graph, and then the correct answer with a little bit of leeway, plus or minus some values, because reading off a graph is actually quite hard to do perfectly accurately. Okay, so let's have a look at the next question. Radium-226 was discovered by Marie Curie in 1898. The notebooks she used were contaminated, not irradiated, contaminated with radium-226 and are still hazardous. Explain why the notebooks are still hazardous. 1898, we've just worked out the half-life. So it's not even one half-life ago. Okay, so since radium has a half-life of 1,650 years, right? And one half-life hasn't even passed. I haven't written that down there. One half-life has not passed. One half-life has still not passed. You can expect more than half the original radioactivity to be present. Okay. Explain how the properties of alpha, beta and gamma radiation affect the level of hazard at different distances. Right, well, the level of hazard from radiation is down to, or is due to the ionizing effect radiation has on the cells in your body, particularly the DNA inside the cells. So ionizing, gamma is the least ionizing, then beta is the next most ionizing, and then the most ionizing is alpha. So usually these things follow a pattern, right? Well, they always follow a pattern with the three types of radiation. Either it's alpha's the most, and then beta's the next, and then gamma's the next one down the list. So alpha's the most ionizing going down to gamma the least ionizing, or it's gamma's the most, in which case it's the most penetrating and it's the fastest. And then as you go up the list, they get less and less and less. So gamma's the fastest, alpha's the slowest, beta's in the middle. Well, it's not in the middle, it's actually much closer to alpha. But gamma's the most penetrating, alpha's the least penetrating. So that's the order, that's the way you remember it. And if you were in my class, you'd have seen the analogy I use with a tennis ball, an air gun pellet, and a laser gun. So what am I going to say for this? So I would say at close range, I would say capital at close range, alpha poses the greatest risk due to its highly ionizing effects. Basically, when something gets ionized, you either rip off or add electrons to it, and that change, if it's in a chemical bond, that will break that chemical bond, and if that's in DNA, that will damage the DNA. So at close range, alpha poses the greatest risk due to its highly ionizing effects. This drops off rapidly due to its low penetrating power, or low range in air is another way of saying that same point. Okay, gamma, on the other hand, is a danger at distance, as it is very penetrating. It is, however, very low in its ionizing power. Full stop. Okay, so beta is exactly in the middle of both of these things. So beta radiation can, well, I can't remember the exact numbers about how far it can travel in air, so I don't want to phrase it. I want to phrase it carefully so I can maybe get a marking point for saying something sensible about beta radiation. So beta radiation has a moderate range and ionizing ability. Therefore, it's a danger at close and moderate range. Okay, so we'll check the mark scheme and see if I've said anything too stupid. So it's 1,600 years, we've got that range, so that's okay. 119 years have passed, so the activity has not dropped by much. I think I've really made those points. And let's see this final one. Alpha is the least penetrating, the most ionizing. Beta is the second most penetrating. So I think, again, if we check the mark scheme on that, I think I'd have hit the marking points for that. Okay, I hope you found this useful. Please comment, like, subscribe, and share.